Well, AP Pre-Calc, we've reached our final day. This is Miss Adams from Flamingo Math. We're going to finish up lesson 14 in chapter 4. It's the end of AP Pre-Calc. We want to look at some more application problems where the transition matrix is a 3x3 regular Markov chain in this last lesson. Let's say we have three companies, A, B, and C. They're in competition with each other. We know the transition matrix T for customers switching every month among them is given in this matrix below. If the initial market share for companies A, B, and C is given by this matrix, we want to know what is the long-term distribution of market share for each company. And we've seen we can do that by taking the matrix T and raising it to some large power. You know, my favorite is the 20th power. So if we raise this matrix to the 20th power, we're going to get 0.2626 repeating for A. So A, B, C is going to be 0.26 repeating. And the B value is going to be 0.27 repeating, 2727, and then 0.46 repeating for C. So the company A is going to have about 26.3 long-term distribution. Company B will have 2727, so 27.3%. And then company C will have 46.4. We're going to round up that tenth to make this 100% when we add all three companies. In example 10, we have a bike share program for a very large city. There's 3 stations where people can borrow a bike or a scooter and return it to any of the 3 stations. The transition matrix is shown at the right, and if the initial distribution of bikes is 40% at station A, let's see, we're going to write this down, S sub, we have 40% at station A, 25% at station B, and 35% at station C. What will be the distribution after 2 days? So to find the first day's distribution, S sub 1, is going to be the initial times P. So we're going to put this in our calculator times P over here. And again, I'm trusting you to do this along with me. I get 0.215, 0.265, and 0.52. Then to find the second day, we're going to take the first day times the matrix at the right and end up with 195, 0.254, and 0.551. So to answer the question, at station A, we're going to have 19.5%. At station B, we'll have 25.4%. And then at station C, we have 55.1%. Make sure that adds up to 100%. 19.5, 25.4, 55.1. What will be the eventual long-term distribution of rides at the station? Using our transition matrix, raising that to the 20th power, it's going to give us the results for A is 1.19562, 19565, so 19.6%. And B was 0.23913, so 23.9% for station B. And then for C, gave us 0.565, something or other, point C, 56.52, so 56.5% for C. Do those add up to be 100%? 19.6, 23.9, and 56.5? Yes, exactly 100%. Part C. If the initial distribution of vehicles at the stations was evenly distributed, will the eventual long-term distribution be different than the initial distribution given in Part A? And the answer to that would be no. Eventually, the steady state is going to be the same. Eventually, the steady state will be the same. Example 11. Let's say that 3 department stores, A, B, and C, are in competition with each other. And we know the following about shopping and market distributions. We have 10% of shoppers at store A will switch to store B every month, and 10% to store C. So let's start off with writing that transition matrix as we go along. So we got A, B, and C. This is where we're starting. And A, B, and C where we're going to. So from A to A, that's 80% since 10% and 10% here. For B, 10% of shoppers B will switch to store A and 20% to store C. So that leaves 70% staying at B. And 20% of store C shoppers will switch to store A, and 20% will switch. We have a typo there. That should be store B. So 20% will switch to store B. Store B, that's going to leave 60% staying there. So we're going to start from here and go to here. What is the stable distribution matrix for part B? What's the stable distribution matrix? We've got A, B, C. We're going to multiply by 0.8, 0.1, 0.1, 0.1, 7, 0.2, 0.2, 0.2, 0.6, and that product has to give us A, B, C. So we can have, let's see, they have us using the calculator, but I want to do it like writing the equation first. Let's try it the old-fashioned way here. So if I write the product here, 8/10 of A, 1/10 of B, and 2/10 of C has to give the A value. 1/10 of A, 7/10 of B, 2/10 of C has to give us B, and 2/10 A plus 2/10 B plus 6/10 C has to give us C. Whoop. I got a boo-boo there. This is 2/10, right? 2, 2, and okay, we got 0.2, 0.2, and 0.6 is C. So to work this out the long way, I'm thinking if I take 10 times row 1 minus row 2, so 10 times each one of these terms gives me this, and 10 times each one of this gives me this, but we want to subtract row 2 from row 1. That gives us 7A minus 6B is 10A minus 10B. Collecting like terms for B, we got 4B is 3A, so B is 3/4 of A. And then to take 2 times row 4 and 10 times row 2 and subtract that from 2 times row 4, we get A minus 5B. C goes away again, so we've eliminated C twice. 2 minus 10B. Collecting like terms for B, we have 5B is equal to 2 minus A, but we know B is 3/4 of A. So if B is 3/4 of A, 5 times 3/4 A is 2 minus A. So A turns out to be 8/19. If A is 8/19, we can go back and substitute for here. And A is 8/19. B turns out to be 6/19. And C turns out to be 5/19. So we have our stable distribution matrix. And I'll need to write that somewhere. So our stable distribution matrix A, B, C. Put the 1/19 outside, and we have A is 8, B is 6, and C is 5. So this is the answer for part B. And what will the eventual long-term distribution percentage for shoppers in each department store look like? So let's finish that up using our transformation matrix at the beginning in our calculator, raising that to the 20th power. Whoop. You can see here we have store A is going to be about 42.1%. Store B is going to be about 31.6%. And then store C is about 26.3%. So we have mastered Markov chains and transition matrices, and we are finished with the full year of AP Pre-Calc. Congratulations.